My name is Alena. I work at Microsoft on Azure, and today we're going to be talking about data-intensive workloads. So what are first things that come to mind? Databases, caches, stream processing systems, any systems that work with state and data. Another type of systems that we're going to be talking about today is not necessarily stateful systems, but those that operate in a way that isn't fully covered by predefined Kubernetes abstractions. So it can be any of the popular distributed systems like Cassandra or Kafka. They definitely need persistence. Or it can be systems like Spark that operate mostly in memory but still require persistence for certain scenarios, like persisting a trained machine learning model. Or it can even be a system that you have built that might need to store state and manage state. It might have very specific lifecycle rules of operation or need to provide certain guarantees like consistency, no data loss, and other similar things. So just a quick show of hands, who here feels like you have more experience with data systems than Kubernetes? Okay, about 60%, I think. Interesting. So majority of information on how Kubernetes is used today, it reflects mostly stateless services. But in some cases, however, it might make sense to run something more complex on Kubernetes. And there is a big difference in technical process of how we run data systems and more complex systems on Kubernetes versus simpler stateless services. And I know that we have a very wide range of audience here. I have looked at the attendee profile and have seen engineers, solution architects, engineering managers, CTOs, open source project maintainers, and others. That's why we will address the topic from various perspectives. First, we're going to talk about making a decision whether or not Kubernetes is good for your systems, about the whys, the risks, the benefits, and challenges. Then we're going to cover existing solutions, how to run data-intensive systems on Kubernetes correctly. And finally, we will talk about the future, what we can expect, what we can already start preparing for. Decision-making is always fun. So if some organization with similar technologies is using Kubernetes, it doesn't always mean that it will work as well for your use case. They might have more resources or expertise. Their risk acceptance barrier could be lower than yours. They also might have different goals. So when making a decision on whether Kubernetes is or isn't a good system for your use case, there are quite a few things to take into account. What issues and challenges you would like to solve that you have in your current environment where you are running those data-intensive systems? Which of those challenges do you think Kubernetes will solve? But then what new challenges will it create that you will have to deal with? How much will it cost? How much benefits will it bring? What changes will need to happen in your team, in your project and organization for it to be successful? And what are the benefits of choosing Kubernetes to run your system over going with a managed service? So it's good to have answers to those questions before making a firm decision, because really only you can answer them. So if you're wondering what are some of the reasons companies are choosing Kubernetes, there are many examples, of course. Some want to achieve better workload portability for their systems, or to benefit from convenience and flexibility of deployment, operations, automation for creating new resources, or to get more independence from various vendors or various providers. Some run it to get faster startup times for new resources and environments for cost savings. But some companies are choosing Kubernetes because they're already running Kubernetes for their existing services, and they want to use it for more of their solutions. A lot of projects find extensible and open API that Kubernetes has very useful for building solutions on top of it. They also prefer to trust it because of open and rapidly growing ecosystem. But on the flip side, there are, of course, quite a few challenges. Some companies might be in a situation where there are no available solutions that satisfy their scenario. And if they decide to go with Kubernetes, they would sometimes have to build their solution almost from scratch because there are no suitable options, to gain new skills, to troubleshoot new environments, and to spend a lot of resources on training and time to support it. There are other challenges like stability and reliability of existing components, integrations with various systems, and many more. But one thing that I can actually say with great certainty is that if something in Kubernetes ecosystem was unstable or didn't exist a few months ago, there is a big chance that it's fixed by now. It's really a fast-growing ecosystem. So how do we determine possible risks and challenges? To do that, we need to understand what Kubernetes can and can't do, what it is and isn't responsible for. How do we determine if Kubernetes can satisfy our guarantees that are required by our system? We need to learn abstractions and instruments that Kubernetes and its API have to guarantee or implement our system requirements. So the big takeaway here is, before we can make the right decision, we have to get more specific and take a look at details. So let's do that. So you all are most likely familiar with at least several built-in Kubernetes types, like pods, jobs, deployments, stateful sets, services, and more. Those and many more are core Kubernetes API objects or types that we can use to build our apps. When new data people are discovering Kubernetes, they see stateful sets. And it might seem like a good solution for running their data systems on Kubernetes. But if we look a little bit closer, stateful set is just one of the many predefined Kubernetes types. It supports certain predefined functionality, like replication, stable pod startup ordering, predictable name for pods, stable links to persistent storage volumes, but nothing else really. It is great for some use cases, but is it really enough for all of the data-intensive system scenarios? In other words, what if stateful sets don't really work for our scenario? Our scenario might need more specific data distribution or lifecycle rules that are not implemented on the level of stateful sets. So what if none of the core Kubernetes types work for our scenario? The reality is, yes, built-in Kubernetes abstractions might not be fully sufficient for running more complex distributed data systems. And it comes down to application-specific things that need special care. Objects like stateful sets are powerful, but they alone have no idea what's different between a Kafka or Cassandra cluster. Even if they have special operations, common operations like scaling, it doesn't have any knowledge if things should be managed differently. Unless we teach Kubernetes how to treat our systems and take nuances specific to stateful application under consideration. So Kubernetes simply doesn't know all of the specifics of internal operation of all distributed systems that we might want to run on it. The definition of operating correctly is different for many different systems. The good news is that we can still run many of the complex systems on Kubernetes correctly, because there is a way to do so with custom resource definitions and custom controllers. So let's make it more concrete and look at a few examples. Let's take cluster scaling as a first example. Many clusters can support scaling, so let's think of it as Apache Kafka cluster for a second. If we're running it using stateful sets and decide to increase number of brokers in the cluster, a stateful set would add a new replica pod, attach a new persistent volume to it, issue it a new predictable name. It isn't actually enough for correct operation of the Kafka cluster. Adding nodes to a Kafka cluster correctly requires a few things. First of all, manually assigning some partitions to new brokers, because just by itself, new pods don't automatically get assigned new topic partitions, so we need to take care of it. Another important thing is cluster configuration. New pods will not automatically be updated with all necessary configuration values. Another example are cluster restarts, which is relevant to many systems, but is very specific to each separate system. So for Kafka, restarts need to be done carefully. So what does it mean to have a good restart? We need to make sure that there are no under-replicated partitions before doing this, and we need to make sure that the cluster is in a healthy state. Then we can start the restart operation and do it one broker at a time, each time making sure that the broker is caught up to the leader. So also graceful shutdown of each broker is very important for this operation. Basically, these are just some examples of what could go wrong if we don't implement it correctly. And because Kubernetes is very extensible and open, we can implement new and missing functionality really easily. We can use custom resource definitions and custom controllers. And a custom resource is an extension of Kubernetes API that is not necessarily available on every Kubernetes cluster. It can be added. So after it's added, users can work with objects of the new resource, just the same way we're working with built-in core objects like pods. So we can think of CRDs as new Kubernetes entities, new data types that we define that become a part of Kubernetes API. But on their own, custom resource doesn't actually contain any logic. It just defines a new resource. But we can combine a CRD with a controller, which allows us to declare logic to say what is the desired state for our resource. For example, we could create a new CRD called a Cassandra cluster, or a Kafka cluster, or a Spark job, or a Tensorflow job. And then we can write a custom controller for our CRD and specify the logic that defines what correct desired state means for operation of our specific stateful application. If we take Cassandra, for example, it could mean that the controller won't let Kubernetes restart a replica pod until the replication of certain data on some partition is complete. So just as each built-in object in Kubernetes has a core controller behind it, custom controllers enable us to create new logic to manage our new CRDs, to extend and add new functionalities. You might have heard of an operator pattern, which is just a combination of a custom resource definition and a custom controller. Operators are interesting because they are important not only for container people, but they are also important for Kafka engineers, for Cassandra engineers, for Spark engineers, TensorFlow engineers, and basically for all engineers who want to benefit from running and managing their distributed systems reliably, consistently, and correctly when built-in Kubernetes resources are not enough. So now that we know what an operator is, we can take a closer look at internal aspect of it. First of all, it's helpful to understand the notion of events in Kubernetes. So an event is an action on some resource. It can be create, update, or delete. And those resource events are stored in the queue. What controller does, it subscribes to the queue, and a controller worker is going to block on a call to get the next item from the queue. So we can think of controllers as brains behind our resources themselves. There is another important aspect that is worth mentioning. It's called an informer. An informer is like a connection between where those events originate from and between our controller. So what informer does, it registers event handlers for these 3 different types of events, add, update, and delete. And inside event handler functions of the informer, we add resource key to the queue to let controller logic handle those events appropriately. So let's take a look at an operator in action. One of the existing operators that I really like is a Tensorflow operator, or TF operator for short. And it is part of a KubeFlow project. KubeFlow project aims to provide a convenient way of running TensorFlow jobs on Kubernetes clusters. And this example actually runs on Azure Kubernetes Service, but you can run it anywhere else if you'd like, because workload portability. And I have already installed KubeFlow on my cluster. That means that the cluster is already aware of the new CRD and custom controller that KubeFlow needs to run TensorFlow jobs. So let's take a look at the example. So first of all, we need to generate the specification that we can use to submit new TensorFlow jobs. And KubeFlow uses KSonnet tool to do generation of such specifications. And here it gave us a path to the specification that we can look at if we copy the file. And inside this file, we can see that this is some TensorFlow specific parameters that we can just use if we want to run the test job. And if you notice that it has TF job kind. So what we can do now is we can deploy this specification to the cluster and start the job using the apply command. So after this is done, I think it would be interesting to look at the CRD in our cluster. So we can take a look at what CRDs exist, and then we can even filter them using the prefix. So I know that the CRD is called TF jobs. And we can even look at more details of what it represents. So it has a kind TF job. It has TensorFlow-specific parameters and properties. For example, replicas can be of different types, like chief, parameter serve, and eval. And there's a lot more information here. But now let's actually check the status of our TensorFlow job that we submitted. So, and we're working with it the same way we would work with a built-in object. But behind the scenes, it uses pods because it is implemented that way. And we see that there are 2 pods behind the scenes, parameter server and a worker. And if we look in the logs behind the worker pod, we will see that our TensorFlow job is running, and it has it is using ResNet 50 model. It is in training mode, and it worked. So once the operator is running, it watches all of the new API requests related to the TF job resources and uses the logic defined in the TF jobs controller to manage TensorFlow jobs based on lifecycle rules. So let's go a little bit deeper behind the scenes and find out how the TF job operator actually works. And the code for it is online. It is really interesting to check it out. The link is below. It's github.com kubeflow /tf-operator. And this is the CRD, custom resource definition example. You can see that kind is TF jobs. And on the flip side, there is also a definition of the type called TF job, which is a struct that we're going to use when controller is going to work with the job. It has 2 fields, job specification and job status. This is important because the controller is going to compare those values and make sure that the job is in the correct status that we specified in our specification. Inside the job specification, there is a map of replica types and replica specifications, because we know that one job can have many replicas. And each replica specification defines, well, how many replicas of a certain type there are, what template is used for replica. And if you were paying attention, that you could see that the pod template specification is used here. And that's why pods are being created behind the scenes. When you're writing your own operator, you can choose your own abstraction or several if you want to use it. And also it has a restart policy for the job as well, for the replica. And here we have additional types to define types of replicas that we're going to work with, restart policies that we're operating, and job status. And here is an interesting part. This is an informer, and it basically watches the events, and it is like a connection between the source where they come from and the controller. And this is the most important part of the operator, which is the controller itself. And it has a function called reconcile TF jobs that checks and updates replicas for each given replica specification. So in case something goes wrong with the job or the replica, it will requeue the job or restart the replica and make sure that the status of our job is correct. So knowing exactly what operators are, how they work, it's useful to know how to build one if you would like to. And you can do it manually using code generators for the client, informer, lister, and writing your own controller. But you can also use things like operator framework by CoreOS that can actually significantly simplify the process. So check that out if you're interested. And then next, a reasonable question comes to mind. Now that there are operators, CRDs, and custom controllers, where can we find all of the operators we need? So, well, there are a lot of existing operators that are open source on GitHub. For example, a Cassandra operator from Instacluster or Tensorflow operator, they are all open source in the list. Some operators are actually closed source or in preview by various companies. For example, check out Confluent operator for Apache Kafka. And some other operators simply don't exist yet. So remember that the CRD concept is relatively new for other than Kubernetes people. And there are a lot of people who work in data industry that are not familiar with Go and don't know everything about Kubernetes. So it takes a bit of time to learn and start creating legit operators. So if you'd like to check out more of the operators, there's a list on GitHub as well. So you'll have to type that link, github.com/operator-framework/awesome-operators. And another important note to add, there is no consistency as for how you can use existing operators. For example, some operator creators choose to use Helm as a main mechanism for end user to work with the operator. Some use case Sonnet, like you have seen with TensorFlow. Some people build custom CLIs, so there is no one single way everybody uses to work with operators. And by the way, even though we're looking at operators from the lens of data and consistency and correctness, the same applies to other aspects of distributed systems, like managing security, custom lifecycle workflows, and other important things. So before we talk about the future, let's summarize some takeaways from this section. So especially for solution architects and engineers, knowing how to build Kubernetes objects, how built-in Kubernetes objects work and how operators work, it will definitely help make better decisions for when Kubernetes is and isn't the right tool. and will help make sure that you're running your data systems on Kubernetes correctly versus just running. So, and this brings us to the next point. You might know everything about CRDs and custom controllers, but if you don't know what correct operation means for the system that you're running, then there won't be much success, because this is one of the reasons current data systems-related operators are being developed through collaboration between Kubernetes experts and particular domain distributed system experts. So now let's talk about the future. Majority of operators for data are in extremely early stage right now. But we already started seeing big progress, and there are new operators coming out one after another. And in the future, there will be more operators that will continue to improve, be more stable, provide better functionality. And as more people start writing operators, we will see further progress on making them easier to write. And Kubernetes is really one of the most extensible systems for running other systems on top of it. It's also becoming really easy to add new storage options, and the quality of performance storage options is getting better. Local volumes is one of the examples. We will see our industry become even more focused to work on better workload portability. For example, Cloud Native Application Bundle, or CNAB, is one of the examples of this work. And we will observe the continuing shift from low-level abstractions to more focus on being effective writing our applications. So things like Metaparticle and Draft, for example, bring our attention back to code. And Helm and Brigade help automate many routine operations. So Kubernetes already runs on any cloud, on premises. It allows us to add missing functionality. And with its powerful foundation layer, it is already on its way to becoming a platform where we run or coordinate most of our systems. Because starting with Open Service Broker as a gateway for managing cloud services and resources from Kubernetes, continuing with operators as a beginning of something that we might call managed service, but not tied to any cloud. And now looking at things like Crossplane for multi-cloud control plane. All of this means that we will have more freedom to decide where and how to run our applications without sacrificing benefits of using alternative systems when appropriate. So based on what you have heard and what you have tried, I would like to learn about your experience with data-intensive systems on Kubernetes, with the purpose to better understand your goals, requirements, and challenges, and make it easier for others in the industry. So you can use the link here, bit.ly/data-k8s, to share your thoughts with me if you would like. I would appreciate that. And some resources, if you're curious to look at my blog, if you're interested as well. There are my previous presentations. And that's me. Again, I'm Alena Hall. I work at Microsoft. If you want to reach me, I am on Twitter at AlenaDroid. And if you want to talk to me, I'll be around here outside of the ballroom after the talk. And also, you can come down to Azure booth in the expo hall. There are a lot of my colleagues who can talk about interesting tools and interesting problems. And I'd love to chat with you. And I'm also on the program committee for Kafka Summit, Kafka Summits next year. So if you would like to submit, I would really encourage you to do that. ML for All is a conference that I organize about machine learning with a few other people. And if you're into machine learning, you can check it out. It should be in Portland next year. And the last thing, just remember that you can do powerful things with Kubernetes, and keep that in mind for your next project. Thank you.